Hello. Okay, there we go. 1, 2, 1, 2. All right, hang on one sec. We should be good now. I just want to see here. Let's scrub to the beginning. Okay, good. We are live. Okay. Sorry about the mic lag. I promise you're not going to have to watch a silent film. Excuse me, lecture. All right, let's go ahead and close that down. Okay. Excuse me. So hello and welcome. I'm not sure why my mic wasn't registering, but I was able to figure it out on the software side. All right, today is lecture day 3. Okay, sweet. Lecture 3, chapter 2. So we are starting chapter 2 officially, where we get to actually start talking about some chemistry. Up to this point, it's all been sig figs and units and all that stuff, which is important. We're going to be doing it, like I've said all along, till the very last day of the semester. But I'm excited because today we actually get to start talking about atoms. We actually get to begin our journey into chemistry, because physics has units. Every physical science has units, has sig figs. But we get to talk about concepts that are distinctly chemical today. Now, this is probably going to be some sort of review, but we just have to go through it to be thorough, and we're going to build complexity as we go. So the first thing that I want to mention is a little bit about subatomic structure. Yeah, science. That has to be the best Jesse Pinkman moment. All right. So we're gonna start with a brief destruction, Freudian slip, a discussion of subatomic structure. And there are 3 subatomic particles that comprise every atom. You need to be aware of them. There are protons. There are neutrons. And there are electrons. Protons are positive. Neutrons are neutral, hence their name. And electrons are negative. All right. In addition, both the protons and neutrons are contained in the nucleus. Which is the center of the atom, and electrons orbit the nucleus. All right. And so that's kind of gives rise to, so for example, a helium atom. Helium has 2 of each, 2 protons, 2 neutrons, and 2 electrons. The protons and the neutrons are located in the center of the atom in the nucleus. So you've got your protons, you've got your neutrons. together, and then the electrons are orbiting the nucleus on the periphery. So this right here, that is the nucleus. And I'm sure, like most of us are familiar with this image and this way of representing atoms, and it does a fairly good job. We're going to dig into what it does well, what it does not do well, in a little bit later in the course. But that's a good kind of starting place, putting us all on the same page. All right. Now, the periodic table of elements contains a wealth of information about each atom, each element that we know of, that we've discovered and or made in nature on the periodic table. So take, for example, everybody's favorite element, silicon. Every element has its own little rectangle with a number above and a number below. All right, and so these three pieces are in every elemental kind of box on the periodic table, and this one right here, this is called the elemental symbol. Elemental symbols are either one or two letters. Usually they're one capital letter. Sometimes they are a capital letter and a lowercase letter. And then up above, you have what is called the atomic number. Which is represented with the symbol capital Z. All right, and the atomic number, actually I'm going to scoot this over just to give myself a little more room to breathe here. Something you should know about the atomic number is the atomic number equals the number of protons that an element has. All right, so that number up above is the number of protons in the nucleus. And then the number down below, right here, this is called the atomic mass. Oh, let me keep my color coding consistent here. This is the atomic mass. All right, and the atomic mass tells you the mass of the proton, and the units are AMU, or atomic mass units. Sometimes these are just called U. I believe your book uses, or our book, I guess I should say, uses U. It says U, and it's the same as AMU. They're both totally correct. I use AMU because I was raised on older textbooks, but I guess they're replacing them with U, but I'm not. All right, now, you may be looking at the information given on the periodic table and going, well, wait a minute. There's a symbol, which is fine. There's the atomic mass, I guess. That will be useful later. But for now, I introduced 3 subatomic particles, protons, neutrons, and electrons. And you can say, I only see protons. Where do I find the neutrons and the electrons? The answer to that question is, well, there's 2 answers because you're asking about 2 different particles. First off, when you're asking about electrons, so in every neutral element, And that means neutral means an element with no net charge. In every neutral element, the number of protons is equal to the number of electrons. All right, so even though technically the atomic number is the number of protons in the nucleus of that element, it also tells you the number of electrons. Because for a neutral element, protons and electrons are equal, and that makes sense because neutral means not charged. So that means for every one positive charge, you also have one negative charge as well. All right, now, if you're still wondering about neutrons, the information on neutrons is not contained on the periodic table. To determine how many neutrons are present in the nucleus of an atom, you need to look up something called the mass number. All right, and the mass number is represented with the symbol A. All right, so A is the mass number, and A, the mass number, is equal to the sum of the number of protons plus the number of neutrons. All right, and this information is not contained on the periodic table. You have to find that elsewhere or be given it. You may be wondering why. Why are protons on the periodic table, but why are neutrons not? And the reason is this. The number of protons in a nucleus is the defining trait for that element, all right? What makes silicon is that it has 14 protons in its nucleus, all right? Silicon can have it's varying number of electrons, varying numbers of neutrons, but silicon will always have 14 protons in its nucleus. If you take a look at the periodic table, all right, carbon, for example, has 6 protons in its nucleus. Any element with 6 protons is automatically carbon. Now, if you're asking, well, what if it has 7? Carbon doesn't have 7. If there are 7 protons in a nucleus, then that element is nitrogen. All right? As the number of protons change, the identity of the element changes with it. So that's why it's included on the periodic table, because the element identity is determined by the proton count. You can have elements, and all elements will have the same number of protons if they're the same element. But you can have elements with the same proton count that have different neutron counts, all right? And that is the definition of an isotope. All right, the definition of an isotope is this. Or I should say isotopes. All right, here's the definition of isotopes. They are elements of, not elements. We need to be precise with our language here. Atoms. Isotopes are atoms of the same element. In other words, they have the same number of protons. Atoms of the same element with different neutron counts. All right, and the way that you depict isotopes, is there's 3 different ways you can show it. One is you can write the elemental symbol, and then to the left of the elemental symbol, you can have the mass number superscripted and the atomic number subscripted. So that's one way you can designate an isotope. Another way you can designate an isotope is you can write the elemental symbol and put a dash and write the mass number. The third way is you can write out the element's name, put a dash, and write the mass number. Here, oops. All right, I'll turn up my mic in a little bit. I can't do a ton though because I don't want to start peeking out the mic and getting feedback. But I will boost it a bit. Okay. So these are the three ways you can designate a specific isotope. So for example, and it may be a little abstract, but for example, if you look at sodium, so there are several different isotopes of sodium, and the isotope of sodium, so this could be one way you depict sodium, 23, or you could write Na-23, or you could write out its name, sodium 23, and that's the name right here. This last category, this doubles as the isotope's name. All right, so no matter which one you're using to depict the isotope, we call this sodium 23. So you say the name of the element followed by the mass number. And these all mean the same thing. This is an element, an atom of sodium. All three of these depict the same thing, which is a sodium atom. If you look it up on the periodic table, sodium has an atomic number of 11. That means they got 11 protons. This is a sodium atom with 11 protons and 12 neutrons. Because remember, the mass number up here is the sum of protons plus neutrons. All right, protons plus neutrons equals the mass number. All right, so let's throw a couple examples up here. Let's see. Okay, so let's go determine the protons, the number of protons, neutrons, and electrons in an isotope of fluorine 19. All right, now to solve this, we're going to need to look at the periodic table and identify where fluorine falls. And fluorine is right here, which is a 9. Nope. Oops. The mass number and the atomic weight are different. The atomic weight is on the periodic table. The mass number is not on the periodic table. So you have to be given the mass number for a specific isotope. You can't look it up because there are multiple isotopes for each element on the periodic table. And so if we included every isotope, it would double or triple in size. So the mass number is different than the atomic mass. The atomic mass is on the periodic table. The mass number is not. All right, so first off, when we are asked to determine the number of protons, neutrons, and electrons, the thing to remember is the periodic table will tell you the number of protons and electrons. There are 9 protons in every fluorine atom because that's on the periodic table. And because neutral elements have the same number of protons and electrons, that means that there are also 9 electrons. All right. Now, for the neutrons, we need to use the mass number together with the atomic number because the mass number is equal to the number of protons plus the number of neutrons. So if we want to find how many neutrons, that means we need to subtract the number of protons from both sides of this equation. So our neutron count for any element that you're calculating this will equal the mass number minus the number of protons, and i.e. the atomic number. All right, so this is 10 minus 9. So we have 10 neutrons in this molecule. Daisy, spot on. P is proton, N is neutron, E is electron. Those are the abbreviations that I'm using. The other ones, atomic number and mass number, I covered on the previous slide. All right. So let's take a look. Okay. So turns out there are 3 different naturally occurring isotopes of carbon. There is carbon 12, carbon 13, and carbon 14. Ariana, you are most welcome. So if you look these up, carbon 12 has 6 protons, carbon 13 has 6 protons, and carbon 14 also has 6 protons. All right, and that's no surprise because they're all carbon. If they're the same element, they're going to have the same proton count. Likewise, they all have 6 electrons to balance their 6 protons. All right. The difference between these isotopes is all in the neutron count, right? So carbon 12 will have 6 neutrons, carbon 13 will have 7 neutrons, and carbon 14 will have 8 neutrons. All right. Now, if you look at so that's the subatomic particle count for each of these elements. Now, if you look at the mass that each isotope has, carbon 12 has a mass of 12.0000 AMU, atomic mass units. Carbon 13 has a mass of 13.0034 AMU, and carbon 14 has a mass of 14.0032 AMU. All right. Now, on the surface of things, so each of these isotopes has a different mass, right? But if you look up the atomic mass of carbon on the periodic table, only one number is listed. So, oh, thank you. So, only one number is listed on the periodic table. How do we get that? Well, the first thing that comes to mind, you might be thinking like, well, we've got three different masses. All of these occur in nature. Maybe the mass on the periodic table is an average of these three naturally occurring isotopes. And you're not wrong, because it is, but it might not be the average you're thinking of. If you look up on the periodic table, if you look up carbon, right, we've got an atomic number of 12. The atomic mass is 12.01. And our units down here are always, they're not ever written on the periodic table, but they're always in AMU. Now you may be going, wait a minute, Josh, you just told me that they were an average, but I'm pretty sure the average of 12, 13, and 14 is not 12.01, right? If you took an average, if you added these three together and divided by 3, the answer would come out to be 13 point something. Definitely not 12.01. So how could you tell me that the atomic mass is an average when it's not the average of these three? Here's the thing about taking averages and the types of averages that they teach, like in middle school and high school. I have a 7th grader stepdaughter who's seventh grade, and so I'm doing all sorts of fun middle school math, including taking averages. Here's the underlying assumption that beneath an average, if you add these three up, divide by 3, you're assuming that all three of these items are present in equal quantities, that it's 1/3 carbon 12, 1/3 13, and 1/3 14. All right? It's not, though. It's not. Turns out these do not have a 33%, 33%, 33% natural abundance in nature. They actually occur naturally in different ratios. Turns out that carbon 12 is present, that 98.93% of all carbon atoms are carbon 12. Of all the carbon atoms that occur in nature, 1.07% of them are carbon 13, the isotope. And of all the atoms that occur in nature, 1 times 10 to the negative 14th% of them are carbon 14. So this number that we get on the periodic table, this is not a pure average. This is what we call a weighted average. It's a weighted average. It takes into account the natural abundance of each element in nature. So that's the reason why this number is closer to 12 than it is to 13 or 14. It's simply because carbon 12 is 98.93. Almost all carbon out there is carbon 12. So the average, when you take that natural abundance into account, is closest to 12. All right, Christian, great question. Christian asks, why are there 3 types of carbon? Isn't it only one element? An element, and so Christian, this is the answer. An element is defined by the number of protons in the nucleus. And you'll notice that for each isotope, carbon 12, 13, and 14, you have the same number of protons. So these are all the same element. The reason why they have different masses is because they have different neutron counts. But changing the number of neutrons in a nucleus doesn't change the chemical behavior of a compound. Changing the protons will, changing the electrons will, but changing the neutrons doesn't affect its chemical reactivity. And so even though there's different masses, they're all part of the same element because elemental identity is based on proton count. And these three isotopes have matching proton counts. All right. Now, we've made it up to, the first kind of challenging problem of the semester. And I don't normally do this, but I'm going to let you know straight up at the beginning that this calculation that I'm about to do is a dead ringer for exam 1. So you will be doing this at least once, possibly twice, maybe more. I haven't written the first test yet, so I can't tell you specifically, but you'll do this problem at least once on the exam. So you want to get good at this. All right, so if you feel that temptation of like, this calculation's hard, maybe I just won't worry about it. Worry about it, get good at it. You're going to face it on exam 1. I'm going to teach you how to calculate a weighted average so that you can, given isotope mass and natural abundance of each isotope, take that information and calculate the atomic mass for any element I throw at you. All right. So let's talk about weighted averages. Let's talk about weighted average. So here's how you take a weighted average. You take the mass, the AMU of isotope 1, and you multiply it by its percent abundance. And then you take the atomic mass of isotope 2, multiply it by its percent abundance, and you do this for however many isotopes you have. Add them all together, and that is how you calculate, that's how you take a weighted average. All right, so if we're going to do this for carbon, we need to multiply each isotope's mass by its natural abundance. The one thing you have to remember, because it may have been a minute since you have used percentages, remember that whenever you multiply a percent by a number, you must, and this really is a must, you must convert that percentage to a decimal. And the way you convert a percent to a decimal is you take whatever that percent is, and you divide by 100. All right, so you're gonna see me in a minute take those natural abundances that I just gave you and put them over 100, and I wanted to let you know explicitly up front, what I'm doing is I'm converting those to decimals. Aseneth, great question. So on the exam, it's you don't have to submit work. It's either multiple choice or numeric entry, and you get it right or you get it wrong, but there's no partial credit. That's not the way I do things when I'm teaching in person, but that's the only way to do things when you're administering exams through Canvas. So you won't have to submit your work. Robert, not when you take a weighted average. You don't have to worry about dividing. Yeah. Asthmatic, you are so totally welcome. All right, let's go ahead and do this, work this problem with the numbers that we were given for the 3 isotopes of carbon, carbon 12, 13, and 14. So first, carbon 12's atomic mass, which again I gave you. You'd have to be given this information. 12.00. You'd have to be given this information if you were asked to calculate the atomic mass on the periodic table, I should say. We have 12.000 AMU is the mass of carbon 12. And we're going to multiply this by, now remember, we take our percentage, 98.93. We put that over 100 because we have to convert that to a decimal. Oops. Yes, Brianna, the short answer to your question is yes. If I'm asking you to calculate the atomic mass for an element, I have to give you the mass of every isotope and its natural abundance. Otherwise, you won't have enough information to solve it. All right, so that is carbon 12. Carbon 13 has an atomic mass of 13.0034 AMU times we take its percent abundance, 1.07, put that over 100. And then we take the atomic mass for carbon 14, 14.0032 AMU. And we multiply this by its natural abundance, 1 times 10 to the negative 14th over 100. All right, and again, remember, our end goal is to add all these up, but before we do the addition, we need to do the multiplication. All right, so when you do the first for carbon 12, it comes out to be 11.8716 AMU. Now, when you look at the sig figs, our percentage only has 4 sig figs. Carbon 12 has, 6. So we got to roll with our fewer number of sig figs, right? The answer to this multiplication can only have 1, 2, 3, 4 sig figs. I'm going to wait around to the end, but I'm putting these lines under the number to remind myself that that I have 4 sig figs in this number. Next, we need to multiply 13.0034 times 1.07 divided by 100. And when, got the hiccups. When we do, the value that we get is 0.139139 AMU. And again, we're going to be limited by our sig figs in our percentage, 1, 2, 3. We can only have 3 sig figs in our answer, so I put those lines underneath. But I'm going to wait around till the very end. Now, when we multiply 14.0032 times 10 to the negative 14th divided by 100, we come out with this number. Let's see. So we have 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 1, 4, 0, 0, 3, 2 AMU. Here we're limited by, again, our percentage, which only has one significant digit. So we can only keep one from this number. I'm going to put that weight around to the end, put that line there to remind myself. And now we're ready to add these three together. All right, when you punch these three into your calculator, the answer you get is 12.01735900140032. That's the correct value. Correct units are AMU. Now when it comes to sig figs, we just did addition. So we take the least precise number, which is, our first one has its last significant digit in the second decimal place. So we must round our answer to the second decimal place. 0 rounds down. So our final answer with the correct number of sig figs will be 12.01 AMU. And that is how you take a weighted average. Now, I have to warn you, that is totally fine. Let's see. Let me just double check to make sure I didn't make a mistake. But either one, the final answer will come out the same. Oh, you know what? I'm double checking my answer right now. And I must have written this down wrong. One 139, 136, 38. You'll notice that even making these changes, we still end up with the same answer. Totally. I wrote down the wrong business. Just let me make a note to myself. All right. Oh, no. No, man. Dude, you never have to apologize for my mistakes. Or trying to learn for that matter. But you never have to apologize to me when I make a mistake. That's just silly. I'm the one who owes an apology to you, really. Okay, so that is how you take a weighted average. This is definitely a problem you want to practice. It will for sure show up on exam 1. Christian, I gave you all these numbers in the original problem. So that's where they came from. All right. So, all right. So the one last thing we have to cover in this chapter before we dive into chapter 3. Chapter 2 is rather brief, but the last thing is something important because after sig figs, this is probably going to be the most used concept that we do that we use in this class. And it all has to do with atom count. All right, it has to do with this concept called the mole. And if you have any chemistry in your background, you've heard this word before, you know it's not a small, blind, burrowing creature. You know it's something far, far worse. Though if you're ever bored, if it's a slow moment, or if you don't know what to do this weekend, a Google image search star-nosed mole. It's an amazing animal that has, like, on its nose, octopus tentacles. It looks something straight out of an H.P. Lovecraft horror story. It's really, really special. Check that out if you're bored. Star-nosed mole. Not what we're going to learn about here, though. A mole is a very important concept in chemistry. And the best way I can think of to describe it is one mole is similar to one pair. All right? One pair is how many things? 2 things, right? There's 2 things in a pair. A mole is like a mole is similar to 1 dozen. All right, 1 dozen is 12 things. 12 things. No worries. Carolina, I was about to just say yes, and then I'm like, wait a minute. It's not 14.0032 times 10 to the negative 15, or to the negative 15. But I had a feeling you just forgot to type in the power of 10. But yeah, spot on. That's the exact same thing. So a pair is 2 things. A dozen is 12 things. A mole is just like either of these. 1 mole is exactly like a pair. It's exactly like a dozen, just way huger. How's that for proper English? 1 mole is 6.022 times 10 to the 23rd things. All right. We use pairs for shoes. We use dozens for donuts or bagels. We don't really use moles for that much because there's few quantities in our life that demand an order of magnitude this high. I think the only thing that I've run into outside of chemistry has to be, I'm pretty sure my wife has a mole of shoes in our closet. I think that's the only thing that I've ever needed this quantity to calculate for, other than atoms, of course. So the reason why we need something this big is because atoms are very, very small. There are trillions upon trillions upon trillions of atoms in everything. And so we need a quantity of things that's gigantic. And that's part of why 1 mole is this large. Now, here's how we can use moles in calculations. All right, so I could ask you, how many atoms are in a 3.2 mole in 3.2 moles of carbon. And the way you answer this is with a unit conversion. So moles is a unit conversion. Right, we know 1 mole is 6.022 times 10 to the 23rd things, which I would add that to your equation sheet for exams. You're definitely going to want that one at the ready. If you want to convert from moles of carbon to atoms of carbon, we need to set up a unit conversion. We put moles in the denominator, moles of carbon. And now, on the previous slide, I said that a mole is 6.022 times 10 to the 23rd things. Those things could be anything. It could be donuts. Wouldn't that be a party? It could be shoes, as is in the case with our shared walk-in closet. Or it could be atoms. So we could say 1 mole of carbon has 6.022 times 10 to the 23rd atoms of carbon. All right? So it's just another unit conversion. That thing could be atoms, it could be ions, it could be molecules, it could be photons, it could be whatever. But because we were asked about, here in this problem, because we were asked about atoms, things, that's what things are in this problem. But things could be anything. You'll notice that the unit moles cancels with moles of carbon. And now we're ready to crunch our numbers. 3.2 times 6.022 times 10 to the 23rd is, my calculator is telling me that my value is 1.92704 times 10 to the 24th. All right, sig figs wise, here's something that's important to note. This number right here, which is called Avogadro's number, he's the dude that discovered it, developed it, is not exact. It is a measured quantity. So this has 4 sig figs, but 3.2 only has 2 sig figs, so our answer is limited to 2. So we count off our first 2 sig figs, 2 rounds down. So our final answer is going to be 1.9 times 10 to the 24th atoms of carbon. And that is the number of atoms contained inside a 3.2 mole sample. All right? Now, let's do another example. Let's do this example. How many moles of copper are in a 5.4 times 10 to the 19th atom sample of copper. All right, how many moles of copper are in a 5.4 times 10 to the 19th atom sample of copper? This is another unit conversion, all right? So we take our 5.4 times 10 to the 19th atoms. And we want to convert between atoms of copper and moles. First, I focus on placing my units. I want atoms to cancel. They go in the denominator. I want to be left with moles. They go in the numerator. And now I add my numbers. 1 mole is 6.022 times 10 to the 23rd atoms. Atoms cancel. And I'm left with some numbers to crunch. So we go 5.4 times 10 to the 19th divided by 6.022. And the value that my calculator is telling me, which is the correct value, is 8.9671 times 10 to the, let's see, times 10 to the negative 5. All right. Moles of copper. Now, how many sig figs can we have? 6.022 has 4. 5.4 has 2, so I can only keep 2. 6, as you'll notice, rounds up, which rounds that 9 up. So this ends up being 9. But I still need 2 sig figs, so this has got to be 9.0 times 10 to the negative 5. Moles of copper. All right, so that is the unit conversion going from atoms to moles. So you know moles, you can find atoms, you can know atoms, you can find moles. How useful is this? I'm going to be real, not useful at all. This is not useful. But it's 1/2 of a useful process. This is 1/2 of a useful process. The reason why I spent time talking about moles and converting from moles to atoms, atoms to moles, is because it's part of something that is actually deeply meaningful. The reason why moles are important in this class is because, so I'm going to tell you something. You're like, why are we doing this? Oh, why is the power negative? It's because it's if you wrote this out in expanded form, this is equal to 0.00090 moles of copper. It's just small, but that's what it is written in scientific notation. Sometimes it's easier to write things in scientific notation, and that's why I have the negative power. But you could also write it out as a decimal, and it's equally valid. They're both of these are correct because they have the same value and they have the same number of sig figs. All right. So why are we doing this? If I just told you that it's not helpful. Yeah, Daisy, anytime. Never hesitate to ask a question if something's not making sense. So why? Here's something that's a bit of a shock. Atoms are small. Atoms are small. They're so small that, believe it or not, you can't see them, and neither can I. We could never count how many atoms are in a sample of anything because we can't even make a pair of tweezers small enough to pick out an individual atom. That's how small they are. We can't measure how many atoms are in a thing. But we can measure mass, right? You could walk into a lab. Well, we can't actually right now because campus is closed. But if campus was open, we could walk into a lab. There are scales there, and we could weigh out a sample of copper, a sample of aluminum, something, right? And we could weigh and determine how much mass is in a sample. I want to show you something. Let's go back to that periodic table. We've got our atomic number above our element. We have our atomic mass below. You know how I told you that the units for the atomic mass are AMU. They are. I wasn't lying. But there's a double meaning here. What I didn't tell you at the time is 1 AMU is equal to 1 gram per mole. It actually gives you a ratio between the mass of something and the moles of that thing. So we could say that carbon has a mass of 12.01 AMU, but that is the same thing as saying that there are 12.01 grams of carbon in 1 mole of carbon. These are the same things. And this is the point. The atomic mass tells you how many grams of an element are contained in a 1 mole sample. The atomic mass tells you the number of grams contained in a 1 mole sample. So even though it's impossible for me to ask any of you to step into a lab and count how many number of, carbon atoms are in a sample, I could ask every one of you to step into lab and tell me how many atoms of carbon are contained a 25.0 gram sample. Brianna, let's talk about it maybe at the end of lecture or once we bump into lab, just because it was a little while ago and we're working a different problem. But lab, there will be some breathing space, even if you're not in tonight's lab. We can do it step by step and work through the issues. So let's come back to it, or we could hit it up in an office hour if you want. All right, but let's do the problem at hand. Which are how many atoms of carbon are in a 25.0 gram sample. Now, this is a unit conversion problem. And every problem that you do going from grams to atoms or atoms to grams will follow the same pattern. To go from grams to moles, you need to look up the AMU. And then moles to atoms, that's the 6.022 times 10 to the 23rd. So, and it's true if you're going in the opposite direction as well. If you start with atoms, you go to moles using Avogadro's number, and then you go from moles to grams using atomic mass units. So here we're given an initial mass to start with, 25.0 grams of carbon. We want to convert from grams of carbon to moles of carbon, because we know once we've converted from moles of carbon, we can convert moles of carbon to atoms of carbon using Avogadro's number, right? We know that 1 mole of carbon, a 1 mole sample, is 6.022 times 10 to the 23rd. All right. Now, to convert from moles of carbon to grams of carbon, you have to look this up on the periodic table. All right. And when you do, you look up the atomic mass, and that tells you that 12.01 grams of carbon are contained in 1 mole. Again, this unit conversion won't be given to you in the problem, but you don't have to memorize it. This is from the periodic table, which will soon become the best friend you have in this class. All right, from the periodic table. Okay, so let's cancel some units. You'll notice that grams of carbon cancels with grams of carbon. We have moles of carbon canceling moles of carbon, leaving us with just atoms, which is good because we're trying to find atoms, right? That's what we're after. Now let's crunch our numbers. 25 divided by 12.01 times 6.022 times 10 to the 23rd. The value my calculator is giving me is 1.25353872 times 10 to the 24th. When you look at your sig figs, we have Avogadro's number has 4. Our atomic mass, sig figs matter, has 4 in the atomic mass. But our starting mass only has 3. So our answer is limited to 1, 2, 3. This 3 is going to round down. And so this will be 1.25 times 10 to the 24th. Atoms of carbon are in that 25-gram sample. This method is incredibly powerful. All right, it's incredibly powerful because it takes something that's easy to do, throw something on a scale, find its mass, and now you can determine the number of atoms. You can count the number of atoms in a sample based on its weight, and you can't count atoms. I can't count atoms, but this method allows us to, even though we lack the ability. It's really, really cool when you think about it. Let's do one more example, and then we'll call it a night. Let's do a unit conversion where we take the number of atoms and calculate its mass. So let's do what mass in grams does a 6.78 times 10 to the 20th atom sample of oxygen have? Something that we'll have to do to look up. You'll have to look up oxygen on the periodic table. So this won't be given to you in the problem, but that's why you have a periodic table handy. Oxygen has an atomic mass of 16.00 grams per mole. All right, that's the number on the periodic table. So, first step, we have 6.78 times 10 to the 20th atoms of oxygen. Next, we need to convert from atoms let me do this a little better. We need to convert from atoms of oxygen to moles of oxygen, and 1 mole of oxygen has 6.022 times 10 to the 23rd atoms present. Next, we need to convert from moles of oxygen to grams of oxygen, and this is the part that comes straight off of the periodic table. 1 mole of oxygen has a mass of 16.00 grams. So now moles cancel moles, atoms cancel atoms, and we're ready to crunch our numbers. Let's see, 6.78 times 10 to the 20th divided by 6.022 times 10 to the 23rd times 16. All right, now my calculator is giving me a value of 1.80139489 times 10 to the negative second. Sig figs wise, 16.00 has 4, 6.022 has 4, but my mass has 1, 2, 3. So my answer can only have 3. So this is going to be 1.80, right? Because 1 is a number that rounds down. Times 10 to the negative second. Grams of oxygen, or if you're not running scientific notation, 0.0180 grams of oxygen. Both of these totally valid. All right. And so that is the final, well, it's the final example I'm going to do. I want to leave you guys with a challenge problem. I'm not going to do this one right now. We don't have enough time to bang through it. We might have. But I think I want to give you something to... I want to leave you with something fun for the weekend. This problem is a step beyond any problem we've done, which means it's an excellent example, an excellent moment to simulate exam-like conditions. I guarantee you, I promise you one thing about my tests. You're going to be faced with problems there on my exams that I have never worked in class. That is I promise, dead ringer. That'll happen on the exam. You're going to see problems that are not in your book and that I did not do in class. The reason why I'm doing it is because I'm not testing your ability to copy me move for move. I'm testing whether or not you understand the problems that I'm working in. So I'm going to be giving you problems that are in slightly different format, but if you understand the ones that I've done, you'll be able to think your way through these. So take this problem, try this problem, look at it as an exam challenge. See if you can figure it out on your own. And then let's talk on office hours. Let's talk on Discord. Let's figure this out together. But here is, so this problem is hard. Harder than anything you've ever done. But if you've understood what we've done to this moment in time, you'll be able to solve it. Let's give this a whirl. Or you will give this a whirl on your own. and I wish you luck. Here's the problem. Determine the number of water molecules contained in 500.0 milliliters of water. Note the density of water is 1.008 grams per milliliter. Here's why this is a good problem. It takes things that we learned today in chapter 2, pushes it a step beyond what we explicitly talked about today, and connects to something we talked about in chapter 1, density. So give this a whirl on your own. And then come talk to me about it. We'll solve it together, and it'll be a good learning experience. Okay, I've got a couple of questions up in the chat. Ariana, you have a question about why did you get... I actually know why. Ariana, when you enter 6.022 times 10 to the 23rd in a denominator, when you're punching that into your calculator, you need to put the whole thing in parentheses. Because if you don't, your calculator thinks the only thing in the denominator is the 6.022. Okay, yeah. You just gotta be sure to put a parentheses around the entire thing. Oh, Brianna, you figured out your thing. Okay, solid. Excellent job. Okay, well, let's go ahead and wrap up lecture there. We'll be back, or I'll be back on for lab for section 62. You have your lab activity 1 tonight. I'll be live on YouTube and Discord. So I'll see you all in a bit. And have a good weekend. Try this challenge problem. It's really good. And this is totally something that could show up on exam 1. So here's a chance to get at it early. All right. Good luck, dudes.